we're going to talk about drag force. Remember, the drag force is essentially air friction. And so when we have drag force, we're going to call that capital D. Okay? And the drag force is dependent on a lot of different variables. Think about it this way, like when a guy jumps out of an airplane. If he didn't have a parachute, he would fall very fast. How do you slow down? Well, you have a parachute. Why does that slow you down? Because the parachute is much bigger than the guy's body. So the amount of area hitting the fluid, in this case the air, slows it down. We also have to worry about how fast you're going. The faster you go, the greater the drag coefficient. The faster you're moving through the fluid. If you ever ride bikes, I ride my bike to work every day, you get up to about 10-15 miles an hour, and then the thing that keeps you going from going any faster than that easily is the air force, the drag force on you. So at first when you're going slow, the air friction doesn't seem to affect you hardly at all. But once you get up to speed, then the air friction becomes very strong. And that actually goes by the velocity squared, so that makes a huge difference. It also has to do with the thickness of the air or whatever medium. If you're trying to move through water, it's a lot harder to move through water than air because it's a whole lot denser. So, the drag force, they have found, is roughly equal to 1/2 C rho A V squared. Now, this is an approximation of drag force. Drag force is actually very complicated. This works in most situations for a general kind of thing, but if you are designing airplanes or boats or something like that, it gets way more complicated than this. But for general purposes, this works pretty well. All right, what is C? C is technically the coefficient of drag. And it has to do with the shape of the object. If you have a square that you're trying to move through the air, you have this big black block face that you're moving through the air, that's pushing a lot of air in front of it. But if instead you take that and you make it pointed, let me draw that better. You make it pointed like they do in trucks nowadays. You make it pointed here. Then the point actually splits the air apart. Instead of pushing the air, you're actually pushing the air around the outside of you. That's why they make it pointed. It's kind of like making rockets. You have a big long rocket that you're going to launch into space. Well, you make the top a point and it pushes through the air a whole lot easier than if you just had a flat top. The friction would be much higher. So that's what that C is that coefficient of drag. It has to do with the shape of the object moving through the air. It also has to do with what the material is made of, how well the air slides by it. Some material is essentially slicker than others, and so the air slides by it very easily. This becomes a big deal in boats. Yacht racing, like America's Cup, they would coat the outside of their boats that go in the water with this very special material, cost a fortune, but they were very rich, that would slide through the water better. It's also true with Olympic swimmers. You see them all wearing these suits nowadays. Those suits are specially designed to reduce this coefficient of drag. It's better than your skin. And so then they said, oh, can you have it covering your whole body because it's actually better in your skin? And then they have rules about, well, how much of it can be covered and all those kind of things. Rho, this is the density of the fluid. If it's air, it's usually the density of the air. This is the cross-sectional area perpendicular to the motion. Okay? So, in this case, for a rocket, what the area would be the area of a circle. Because that's how big or how much is moving through the thing. It doesn't matter how long it is. You can make it as long as you want. All that matters for friction is how big that is. All right? So long, skinny tubes are way more efficient than big, fat, wide ones. Same thing here. This would be a rectangle. It would be the area of the rectangle moving through the air. So it's in the direction of travel. It's perpendicular. If you take a perpendicular slice towards the direction of travel. And then v, of course, is your velocity squared. This is what I'm talking about. That's why quickly this term becomes the biggest term here. Because your velocity at first might be very small, doesn't affect it much, but as soon as this gets very high, that becomes the dominant term here and your drag gets very high. All right, let's talk about a specific situation. Let's say you jump out of an airplane. So here you are flying down. Yeah. There becomes a point where the drag velocity, which is, I'm going to draw a free body diagram here. Drag is opposing your motion. Gravity is trying to accelerate you. If we had no air, and you jumped out of an airplane, you would accelerate all the way until you hit the earth, and you just keep getting faster and faster and faster until you impact the earth. But that's not what happens if you jump out of an airplane. What happens is gravity wins at first because the drag force is very low because the velocity is low. But then as you quickly accelerate, the drag force becomes very high, and you get to a point where these equal each other. We call that the terminal velocity. Terminal velocity is where the drag force is equal to the gravitational force. So we can solve for that. Let's solve for what the terminal velocity is. So we know what d is. We're given it, it's right here. So this becomes 1/2 c rho a v squared is equal to mg. If I want to solve for the velocity, then the velocity is just going to be equal to 2mg over c rho a, and you take the square root of that whole thing. We call that your terminal velocity. That is how fast you will go if you just jump out of an airplane. And once you reach that speed, you won't go any faster. Now notice it's a function of your area. So skydivers that jump out of airplanes vary their speed by adjusting their area. You jump out and you spread your arms and legs, you create the most area. And so as you're falling with your arms and legs out, that's your slowest terminal velocity. With all your arms and legs and everything out, you're only going about 150 miles an hour. Give or take, depends on how much, whether you have a suit on or what kind of thing. But basically about that. However, if you go head first and you put your arms at your side, you can get this up to about 300 miles an hour because you've shrunk the area going down. And so that's how skydivers, when they jump out and they want to meet together, they don't jump out at the same time. Lots of times they'll say, oh, here you see the skydiver falling over here. This guy will shorten his area to speed up, and then when he gets down to here, he'll spread out until they all balance, and then they can hook up and do designs, and they all spread out and go float down. Okay? So this is how it works. In fact, terminal velocity for some animals is actually at a speed that they can survive, like an ant. If you take an ant and you throw it out of a building, even tallest building in the world, it'll fall all the way down, hit the ground, and just walk off. Why? Because its mass is so low relative to its area that its terminal velocity is small enough that it can survive the impact. And that only works for very, very light animals. Usually insects can get away with that. They can fall from any height they want, and it won't hurt them. So that's your terminal velocity. That's only the case where you're free falling so that the drag force is equal to gravity. Most of the time you're going to put in these values right here. And you'll be given these different values. And let's do an example of those in the next one.